Previous videos covered an outstanding algorithm for the selection problem, the problem of computing the ith order statistic of a given array. That algorithm, which we called the R-select algorithm, was excellent in two senses. First, it's super practical, it runs blazingly fast in practice. But also, it enjoys a satisfying theoretical guarantee. For every input array of length n, the expected running time of R-select is big O of n, where the expectation is over the random choices of the pivots that R-select makes during its execution. Now, in this optional video, I'm going to teach you yet another algorithm for the selection problem. Well, why bother, given that R-select is so good? Well, frankly, I just can't help myself. The ideas of this algorithm are just too cool not to tell you about, at least in an optional video like this one. The selection algorithm we'll cover here is deterministic. That is, it uses no randomization whatsoever, and it's still going to run in linear time, big O of n time, but now in the worst case for every single input array. Thus, the same way merge sort gets the same asymptotic running time, big O of n log n, as quicksort gets on average, this deterministic algorithm will get the same running time O of n as the R-select algorithm does on average. That said, the algorithm we're going to cover here, well, it's not slow. It's not as fast as R-select in practice, both because the hidden constants in it are larger, and also because it doesn't operate in place. For those of you who are feeling keen, you might want to try coding up both the randomized and the deterministic selection algorithms and make your own measurements about how much better the randomized one seems to be. But if you have an appreciation for brilliant algorithms, I think you'll enjoy these lectures nonetheless. So let me remind you the problem. This is the ith order statistic problem. So we're given an array. It has n distinct entries. Again, the distinctness is for simplicity. And you're given a number I between 1 and n. You're responsible for finding the ith smallest number, which we call the ith order statistic. For example, if I is something like n over 2, then we're looking for the median. So let's briefly review the randomized selection algorithm. We can think of the deterministic algorithm covered here as a modification of the randomized algorithm, the R-select algorithm. So when that algorithm is passed an array with length n, and when you're looking for the ith order statistic, as usual there's a trivial base case, but when you're not in the base case, just like in quicksort, what you do is you're going to partition the array around a pivot element p. Now, how are you going to choose p? Well, just like quicksort, in the randomized algorithm, you choose it uniformly at random. So each of the n elements of the input array are equally likely to be chosen as the pivot. So call that pivot p. Now do the partitioning. Remember, partitioning puts all of the elements less than the pivot to the left of the pivot. We call that the first part of the partitioned array. Anything bigger than the pivot gets moved to be right of the pivot. We call that the second part of the array. And let j denote the position of the pivot in this partitioned array. Equivalently, let j be what order statistic the pivot winds up happening to be, right? So if we happen to choose the minimum element, then j is going to be equal to 1. If we happen to choose the maximum element, j is going to be equal to n, and so on. So there's always the lucky case, chance 1 in n, that we happen to choose the ith order statistic as our pivot. So we're going to find that out when we just notice that j equals I. In that super lucky case, we just return the pivot and we're done. That's what we were looking for in the first place. Of course, that's so rare, it's not worth worrying about. So really the two main cases depend on whether the pivot that we randomly choose is bigger than what we're looking for or if it's less than what we're looking for. So if it's bigger than what we're looking for, that means j is bigger than I. We're looking for the ith smallest. We randomly chose the jth smallest. Then, remember, we know that the ith smallest element has to lie to the left of the pivot element in that first part of the partitioned array. So we recurse there. It's an array that has j minus 1 elements in it, everything less than the pivot, and we're still looking for the ith smallest among them. In the other case, this was the case covered in a quiz a couple videos back, if we guess a pivot element that is less than what we're looking for, well then we should discard everything less than the pivot and the pivot itself. So we should recurse on the second part of A, stuff bigger than the pivot. We know that's where what we're looking for lies. And having thrown away j elements, the smallest ones at that, we're recursing on an array of length n minus j. I'm looking for the I minus jth smallest element in that second part. So that was the randomized selection algorithm, and you'll recall the intuition for why this works is random pivots should usually give pretty good splits. So the way the analysis went is we showed that each iteration, each recursive call, with 50% probability we get a 25-75 split or better. Therefore, on average, every 2 recursive calls, we are pretty aggressively shrinking the size of the recursive call, and for that reason we should get something like a linear time bound. We do almost as well as if we pick the median in every single call, just because random pivots are a good enough proxy of best case pivots of the median. So now the big question is, suppose we weren't permitted to make use of randomization. Suppose this choose a random pivot trick was not in our toolbox. What could we do? How are we going to deterministically choose a good pivot? Okay, so let's just remember quickly what it means to be a good pivot. A good pivot is one that gives us a balanced split after we do the partitioning of the array. That is, we want as close to a 50-50 split between the first and the second parts of the partitioned array as possible. Now, what pivot would give us the perfect 50-50 split? Well, in fact, that would be the median. But that seems like a totally ridiculous observation because we canonically are trying to find the median. So previously we were able to be lazy and we just picked a random pivot and used that as a pretty good proxy for the best case pivot. But now we have to have some subroutine that deterministically finds us a pretty good approximation of the median. And the big idea in this linear time selection algorithm is to use what's called the median of medians as a proxy for the true median of the input array. So when I say median of medians, you're not supposed to know what I'm talking about. You're just supposed to be intrigued. Now let me explain a little bit further. Here's the plan. We're going to have our new implementation of ChoosePivot, and it's going to be deterministic. You will see no randomization on this slide, I promise. So the high-level strategy is going to be we're going to think about the elements of this array like sports teams, and we're going to run a tournament, a 2-round knockout tournament, and the winner of this tournament is going to be who we return as the proposed pivot element. Then we'll have to prove that this is a pretty good pivot element. So there's going to be 2 rounds in this tournament. Each element, each team is going to first participate in a world group, if you will. So there will be small groups of 5 teams each, 5 elements each. And to win your first round, you have to be the middle element out of those 5. So that'll give us n over 5 first round winners. And then the winner of that second round is going to be the median of those n over 5 winners from the first round. Here are the details. The first step isn't really something you actually do in the program, it's just conceptually. So logically, we're going to take this array capital A, which has n elements, and we're going to think of it as comprising n over 5 groups with 5 elements each. So if n is not a multiple of 5, obviously there'll be one extra group that has size between 1 and 4. Now for each of these groups of 5, we're going to compute the median, so the middle element of those 5. Now for 5 elements, we may as well just invoke our reduction to sorting. We're just going to sort each group separately and then use the middle element, which is the median. It doesn't really matter how you do the sorting because after all there's only 5 elements, but you know, let's use merge sort. What the heck. Now what we're going to do is we're going to take our first round winners and we're going to copy them over into their own private array. Now this next step is the one that's going to seem dangerously like cheating, dangerously like I'm doing something circular and not actually defining a proper algorithm. So C, you'll notice, has length over n over 5. We started with an array of length n. This is a smaller input, so let's recursively compute the median of this array capital C. That is the second round of our tournament. Amongst the n over 5 first round winners, the n over 5 middle elements of the sorted groups, we recursively compute the median. That's our final winner, and that's what we return as the pivot element from this subroutine. Now I realize it's very hard to keep track of both what's happening internal to this ChoosePivot subroutine and what's happening in the calling function of our deterministic selection algorithm. So let me put them both together and show them to you cleaned up on a single slide. So here is the proposed deterministic selection algorithm. So this algorithm uses no randomization. Previously, the only randomization was in choosing the pivot. Now we have a deterministic subroutine for choosing the pivot, and so there's no randomization at all. I've taken the liberty of inlining a ChoosePivot subroutine. So that is exactly what lines 1, 2, and 3 are. I haven't written down the base case just to save space. I'm sure you can remember it. So if you're not in the base case, what did we do before? The first thing we did was choose a random pivot. What do we do now? Well, we have steps 1 through 3. We do something much more clever to choose a pivot. And this is exactly what we said on the last slide. We break the array into groups of 5. We sort each group, for example, using merge sort. We copy over the middle element of each of the n over 5 groups into their own array capital C. And then we recursively compute the median of C. So when we recurse on select, we pass it the input C. C has n over 5 elements, so that's the new link. That's a smaller link than what we start with, so it's a legitimate recursive call. We're finding the median of n over 5 elements, so that's going to be the n over 10th order statistic. As usual, to keep things clear, I'm ignoring stuff like fractions. In your real implementation, you would just round it up or down, as appropriate. So steps 1 through 3 are the new ChoosePivot subroutine that replaces the randomized selection that we had before. Steps 4 through 7 are exactly the same as before. We've changed nothing. All we have done is ripped out that one line where we chose the pivot randomly and pasted in these lines 1 through 3. That is the only change to the randomized selection algorithm. So the next quiz is a sanity check that you understand this algorithm, at least not necessarily why it's fast, but at least just how it actually works. And it only asks you to identify how many recursive calls there are each time. So for example, in merge sort, there's 2 recursive calls. In quicksort, there's 2 recursive calls. In rselect, there's 1 recursive call. How many recursive calls do you have each time outside of the base case in the deselect algorithm? All right, so the correct answer is 2. There are 2 recursive calls in deselect. And maybe the easiest way to answer this question is not to think too hard about it and literally just inspect the code and count, right? Namely, there's 1 recursive call in line 3, and there's 1 recursive call in either 6 or 7. So quite literally, there's 7 lines of code, and 2 of the ones that get executed have a recursive call. So the answer is 2. Now, what's confusing is that in the couple of things. First, in the randomized selection algorithm, we only had 1 recursive call. We had the recursive call in line 6 or 7. We didn't have this one in line 3. That one in line 3 is new compared to the randomized procedure. So we're kind of used to thinking of 1 recursive call using the divide and conquer approach to selection. Here we have 2. Moreover, conceptually, the role of these 2 recursive calls are different. So the one in line 6 or 7 is the one we're used to. That's after you've done the partitioning, so you have a smaller subproblem, and then you just recursively find the residual order statistic in the residual array. That's sort of the standard divide and conquer approach. What's sort of crazy is this second use of a recursive call, which is part of identifying a good pivot element for this outer recursive call. And this is so counterintuitive, many students in my experience don't even think that this algorithm will halt. They sort of expect it to go into an infinite loop. But again, that's sort of overthinking it. Okay, so let's just compare this to an algorithm like merge sort. What does merge sort do? Well, it does 2 recursive calls, and it does some other stuff. Okay? It does linear work. That's what it does to merge. And then there are 2 recursive calls on smaller subproblems, right? No issue. We definitely feel confident that merge sort is going to terminate because the subproblems keep getting smaller. What does deselect do if you squint? So don't think about the details. Just at a high level, what is the work done in deselect? Well, there are 2 recursive calls. There's the one's in line 3, one's in line 6 or 7. But there's 2 recursive calls on smaller subproblem sizes. And it does some other stuff. It does some stuff in steps 1 and 2 and 4. But whatever. Those aren't recursive calls. It does some work. 2 recursive calls in smaller subproblems. It's got to terminate. We don't know what the runtime is, but it's got to terminate. Okay? So if you're worried about this terminating, forget about the fact that the 2 recursive calls have different semantics. And just remember, if ever you only recurse on smaller subproblems, you're definitely going to terminate. Now, of course, who knows what the running time is? I owe you an argument about why it would be anything reasonable. That's going to come later. In fact, what I'm going to prove to you is not only does this selection algorithm terminate, run in finite time, it actually runs in linear time, no matter what the input array is. So whereas with rselect, we could only discuss its expected running time being linear, we showed that with disastrously bad choices for pivots, rselect can actually take quadratic time. Under no circumstances will deselect ever take quadratic time. So for every input array, it's big O of n time. There's no randomization because we don't randomly do anything and choose pivot. So there's no need to talk about average running time. Just the worst case running time over all inputs is O of n. That said, I want to reiterate the warning I gave you at the very beginning of this video, which is if you actually need to implement a selection algorithm, this one wouldn't be a disaster, but it is not the method of choice. So I don't want you to be misled. As I said, there were 2 reasons for this. The first is that the constants hidden in the big O notation are larger for deselect than for rselect. That will be somewhat evident from the analyses that we give for the 2 algorithms. The second reason is, recall we made a big deal about how partitioning works in place, and therefore quicksort and rselect also both work in place, that is with no real additional memory storage. But in this deselect algorithm, we do need this extra array C to copy over the middle elements, the first round winners, and so that extra memory, as usual, slows down the practical performance. One final comment. So for many of the algorithms that we cover, I hope I explained them clearly enough that their elegance shines through, and that for many of them you feel like you could have come up with it yourself, but if only you'd been in the right place at the right time. I think that's a great way to feel and a great way to appreciate some of these very cool algorithms. That said, linear time selection, I don't blame you if you feel like you never might have come up with this algorithm. I think that's a totally reasonable way to feel after you see this code. If it makes you feel better, let me tell you about who came up with this algorithm. It's quite old at this point, about 40 years, from 1973. And the authors, there are 5 of them, and at the time this was very unusual. So Manuel Blum, Bob Floyd, Von Pratt, Ron Rivest, and Bob Tarjan. And this is a pretty heavyweight lineup. So as we've discussed in the past, the highest award in computer science is the ACM Turing Award, given once each year. And I like to ask my algorithms classes how many of these authors do they think have been awarded a Turing Award. I've asked it many times. The favorite answer anyone's ever given me has been 6, which I think is, in spirit, should be correct. Strictly speaking, the answer is 4. So the only one of these 5 authors that doesn't have a Turing Award is Von Pratt, although he's done remarkable things spanning the gamut from co-founding Sun Systems to having very famous theorems about, for example, testing primality. But the other 4 have all been awarded the Turing Award at some point. So in chronological order, so the late Bob Floyd, who was a professor here at Stanford, was awarded the 1978 Turing Award. Both for contributions to algorithms, but also to programming languages and compilers. So Bob Tarjan, who, as we speak, is here as a visitor at Stanford and has spent his PhD here and has been here as a faculty at other times, was awarded it for contributions to graph algorithms and data structures. We'll talk some more about some of his other contributions in future courses. Manuel Blum was awarded the Turing Award in '95, largely for contributions in cryptography. And many of you probably know Ron Rivest as the R in the RSA crypto system. So he won the Turing Award along with Shamir and Edelman back in '02. So in summary, if this algorithm seems like one that might have eluded you even on your most creative days, I wouldn't feel bad about it. This is a quite clever algorithm. So let's now turn to the analysis and explain why it runs in linear time in the worst case.